Hi everybody. I'm sorry I have to miss class today, but one nice benefit to that is that you'll be able to stop and pause me at any time as we talk about our introduction to chapter 6 in the Schrodinger equation. So Erwin Schrodinger actually had been working on the Schrodinger equation, but he was frustrated because he couldn't think of a way to include relativistic particles in it. That took Dirac later. So what he ended up doing was he went on a weekend, a romantic weekend getaway, and over the course of the weekend he decided that he would just go ahead and publish what he had, which was the Schrodinger equation as we now know it. Your undergraduate quantum mechanics course is all based on his equation, and the solution to the Schrodinger equation for the hydrogen atom, totally explaining the successes and failures of the Bohr model. So I think we're all pretty glad at this point that he just decided to go ahead and publish, even though he couldn't include relativity. He was an American physicist. He died in 1961, and of course he's one of the creators and architects of quantum mechanics. So the Schrodinger equation is shown here. It's negative h bar squared over 2 times the mass of your particle is equal to the second derivative of the wave function in space plus the potential energy that the particle is subjected to, u, times that wave function again, and then that's all equal to the energy of the particle times the wave function. Okay, so it's for a particle of mass m moving in one dimension here. This is just the one dimension. Of course, Schrodinger's equation was in 3 dimensions, but we're going to concentrate on one for now. And it's a particle subjected to a steady state or non-time dependent potential energy U of x. So this is the time independent Schrodinger equation. Now, of course, there's a time dependent Schrodinger equation, and there's a 3-dimensional time dependent Schrodinger equation, but we'll talk about those a little bit later. Now, this is a differential equation, so this is one of the reasons that we highly suggest that physics majors get that mathematics course, MAT 3130 differential equations, done. But what I'm going to take you through today is just solutions to the equation. So we're going to plug various wave functions, suggested wave functions, into this equation. So we're not asking you to solve it at this time, just be able to take the derivatives and plug in and show that it is a solution to this equation, so don't panic yet. All right, now there's certain restrictions on the wave functions that satisfy the Schrodinger equation. First of all, the wave function must be continuous. Also, the derivatives, the first derivatives of the wave functions, must be continuous for finite values of the potential energy. One of the wave function potentials that we're going to go over today is the infinite square well, and so that one's going to kind of go out the window, all right? But it should be noted that the infinite square well isn't a very physical potential, it's just an approximation. Any real potential is going to have a wave function that satisfies that the derivative of the wave function is continuous. The wave function has to go to 0 as the position goes to plus or minus infinity. That's a restriction. It can't blow up at an infinity. This restriction is because, of course, this is related to the probability, and the probability that a wave function goes to infinity away should not blow up. That's bad. Your wave function must be normalized. This means that if you integrate the absolute value squared of your wave function over all space, that has to go to 0. That has to go to 1, I'm sorry, and that's because the probability has to be 1 that the particle is somewhere. We talked about that last time. The wave function can be complex or real, and the solution is going to depend upon the system. And the wave function has to be defined at all points in space, and it has to be single valued. A particle cannot be of 2 minds about where it should be, in other words. So it must have only one value for each value of x. So those are some of the restrictions on the wave function. Now, I should note that the Schrodinger equation is kind of like F equals ma. It's not something that you can derive from something else. It's a fundamental equation that describes new physics. Now, you can justify it in your head, and you can justify it with math. This isn't the same as deriving it, okay? It's not the same idea. And you can experimentally prove it. In fact, it's been experimentally proven time and time and time again. Now, here's another thing. The idea of a wave function means that the particle is interacting with the environment. Okay, so you'll notice that in that Schrodinger equation, the potential energy that the particle is subjected to is front and center. Okay, so that means that the particles, just like a classical wave would, somehow kind of know what the environment is like, even when they haven't gotten there yet, which is sort of mind-boggling, but also something that goes along with a particle being a wave. Okay, so here's that justification of the Schrodinger equation that I talked about. So let's say that we know that particles are waves, all right? We know that particles are waves. So that means that you can write that wave function as, say, a sinusoidal function. So let's take a really simple one in the steady state with no time dependence and just say that our wave function is some amplitude times the sine function of 2 pi x over lambda, which is just straight up kx, sine kx. So it's a very standard choice. So let's see if it fits into that Schrodinger equation. To do that, we're going to have to take a couple of derivatives of our wave function. So the first derivative of our wave function gives us minus 2 pi over lambda times a times cosine of 2 pi x over lambda. The derivative of a sine is a cosine, right? Then the Schrodinger equation is the second derivative of that. So let's take another derivative of it, and then we get minus 2 pi over lambda squared times a sine 2 pi x over lambda. Now, remember a couple of points that we've already discussed. First, the wavelength, lambda, is equal to Planck's constant h divided by our momentum p. So we can rearrange that to be p is equal to h over lambda, or remembering that h bar is h over 2 pi, then p is equal to 2 pi h bar over lambda. So our kinetic energy, p squared over 2m, or 1/2 mv squared, these expressions are equivalent, would then be equal to 4 pi squared h bar squared over 2m lambda squared. And that's our kinetic energy. So the 2 pi over lambda quantity squared that showed up in that second derivative of our wave function, that can be set equal to our kinetic energy times 2 times the mass over h bar squared. Okay? So we've related our lambda squared expression to the kinetic energy. Okay, now, if we rewrite that, we can say the second derivative of the wave function with respect to the position x is equal to negative 2m over h bar squared times the kinetic energy k times psi of x, our wave function. All right, now let's remember our definition of mechanical energy. The mechanical energy is always the sum of the kinetic and the potential energies, k plus u. So if we rearrange that, then k is equal to the energy minus the potential energy, E minus u. So now let's plug that in. That means that the second derivative of our wave function with respect to our position is equal to minus 2m over h bar squared times E minus u times our wave function. And then you can rearrange that to obtain the Schrodinger equation, okay? So this is a justification. It's showing that it can be true for a really type of standard wave function. It's not at all a derivation, okay? Because I said this can't be derived. It's a new fundamental equation. But it does sort of show you how he came up with the idea for it in the first place, all right? So this is our Schrodinger equation. Okay, now, I did that lecture on complex variables, remember? So I talked about Euler's identities. And we talked about how e to the I theta can be written in the Euler identities as a sum of cosine theta plus I sine of theta, or if it's e to the minus I theta, cosine theta minus I sine of theta. So what that means is that if you have a natural exponential e and you raise it to I times something, then that means it's a sinusoidal function. So this is going to be exploited throughout this lecture. If you have e to the I something or another, then you've got an oscillating wave function. All right, so we're going to use this expression time and time again. Try and remember it. Okay, let's go to the Schrodinger equation and start solving it. Okay, let's start solving it. The most simple potential that something can be subjected to, the most simple potential energy that something can be subjected to, is no potential energy at all. In other words, it's free. Okay, in that case, we're going to set our potential energy u of x equal to 0. That's it. That means that our total energy, E, is equal to just our kinetic energy, which, since the Schrodinger equation is a classical equation, remember, he couldn't fit relativity into it, okay? So since the Schrodinger equation is a classical equation, if U is equal to 0, that means that our total energy is equal to our kinetic energy, which can be written 1/2 mv squared, or the momentum squared over 2 times the mass, p squared over 2m. All right, now, we've said that e to the I something or another is a sinusoidal function because of the Euler identities. So let's just guess, okay, that a free particle would just be a sine wave, right? It's a wave, so a sine wave is the simplest thing that we've got, sinusoidal wave. The simplest way to write that mathematically is our guess, psi of x is equal to some amplitude a times e to the I kx, right? So that's a sinusoidal function. Here a is our amplitude of oscillation. Now in general, the constants for wave functions can be complex numbers, okay? In general they can. They don't have to be, but they can. And remember that k is our wave number, which is 2 pi over lambda. And in a previous lecture, we showed this again and again, that the momentum p is equal to h bar times k. Okay? All right. So, differential equations 101. If you want to see if something is a solution to a differential equation, you plug it in and you try it. All right, so let's take our guess, a e to the I kx for a free particle, and plug it into the Schrodinger equation. So what we have to do is take two derivatives of that expression, okay? So minus h bar squared over 2m times the second derivative of the wave function with respect to x would be equal to, let's take one derivative first, minus h bar squared over 2m times the derivative, and then here's my first derivative of a e to the I kx. Remember, the derivative of an exponential, like e to the I kx, is just the exponential again. So here we have aik e to the I kx. That's the first derivative of psi of x. But we need to take two, so let's take another one, and we get minus h bar squared over 2m is equal to I squared k squared a to the e I kx. Okay, I squared is minus 1. Alrighty, so here we get, that's a typo, sorry. We get h bar squared k squared over 2m times our wave function back again. Okay, the minus sign cancels out with the I squared inside. And then that's equal to, remember h bar k is p, that's equal to p squared over 2m times our wave function, which is equal to the kinetic energy times psi. Okay, so here we have our Schrodinger equation. Remember, our Schrodinger equation was minus h bar squared over 2m times the second derivative of the wave function plus u is equal to e, right? And so here we have the solution. It shows that it is a solution. So psi of x is equal to a e to the I kx is the solution for a free particle. Okay, we plugged it into the Schrodinger equation. We tried it. It works. All right. So you might need to pause it and go back over that a couple of times just to make sure that you understand. Okay, the math is not easy here, but it can be followed if you pause, think, and try again. All right, remember you can pause me. Okay, next simplest potential. All right, this is the canonical example for quantum mechanics. Particle in a box, okay? Particle in an infinite square well. In fact, one of my physics grad student colleagues way too long ago dressed up as a party girl in an infinite square well for Halloween one year. He dressed up in drag, put his hair up in a ponytail on the side, put on way too much makeup, and built a square well around himself. And that was his Halloween costume. So if you're looking for a really corny one for next year, there you have it. All right. So here's your particle in a box. You have a particle confined to a one-dimensional region of space. Okay, we're just going to do 1D here. There's the 3D analogy, which we'll talk about later, but for now we're 1D. The particle is basically just bouncing back and forth between these walls. Okay, we're going to call the length of the wall L, or the length of the box L. Okay, so what would the potential energy be for this particle in an infinite square well? All right. Well, the simplest thing to do is just to make it a square. So basically, your potential energy goes to infinity at the walls of the box, all right? And it's infinite outside the box, and then it's 0 inside the box. So U is equal to 0 for 0 to L, and U is equal to infinity outside the box. That's our potential energy function. Okay, differential equations 101. How do you solve a differential equation? You make an educated guess as to what the solution would be. And then you plug it in and you try it. And if it works, then you apply what are called the boundary conditions and you get the full solution. Okay, so there you go. I just saved you a full semester of differential equations. That's what they're going to tell you time and time and time again in differential equations. And then they're just going to say, how do you make an educated guess? What are educated guesses for certain scenarios? That's differential equations. Okay, there you go. Well, here's our educated guess for the particle in the box. Since the walls are impenetrable, the potential is infinite. There's no way that you can make it through. That means that there's a 0 probability of finding the particle outside the box. What does that mean? Well, that means that the wave function has to be 0 outside the box, right? So psi of x is equal to 0 for x less than 0 and x greater than L. Now, here's another tip from me to you in differential equations. You can always set the solution equal to 0 and it will be true trivially, okay? So a 0 solution is always going to be a nice solution to a differential equation, and then you have 0 equals 0. Always true, always checks out, all right? So for outside the box, the wave function is 0. I can tell you, I guarantee you, that'll satisfy our differential equation. All right, now inside the box is a different story. Inside the box, the potential energy is equal to 0. Now this is really similar to our free particle solution. So what we're going to do is we're going to try our free particle solution again. That's going to be our guess. We've already tried it for u is equal to 0 and it worked, okay? So basically all we have to do is apply our boundary conditions. And when we apply our boundary conditions, we're good. Now what are our boundary conditions, okay? Well, we want the wave function to be continuous everywhere. In order for the wave function to be continuous everywhere, then that means that the wave function has to go to 0 at the boundaries, because the wave function is 0 outside the box. So at the boundaries of the box, the wave function needs to be 0 in order for a continuous solution to be true. So our boundary conditions are that at the walls of the box, the wave function is 0. That means if the box runs from x equals 0 to L, then that means at x equal to 0, the wave function must be 0. And at x equal to L, the wave function must be 0. Those are our boundary conditions. Okay, that's it. Okay, so we know our solution works. Okay, so our solution is the free particle solution. Psi is equal to some constant a times e to the ikx. That's sinusoidal. All right. Now we know from the Euler identities that e to the ikx is a sum of sine and cosine functions. I've told you that your constant a has to be some kind of constant, but it doesn't necessarily have to be real. It can be complex. So since we know that our exponential is sines and cosines, we can rewrite a e to the ikx and say that it's a sum of sine and cosine functions, right? Now I'm going to call these constants in front of the sine and in front of the cosine a1 and a2. And they can be real or they can be complex, okay? These constants, we don't know yet. We haven't solved for them yet, but they're there, all right? So this is our wave function that we're going to apply our boundary conditions to. So we set that wave function, psi, x equal to 0. We set it equal to 0 at that point, x equal to 0. Now, if we do that, then we have a1 times the sine of 0 plus a2 times the cosine of 0. All right? Now, sine of 0 is 0. So that means that we end up with a2 times the cosine of 0. Cosine of 0 is 1. So that means that psi at x equal to 0 is equal to a2. But we're saying that the wave function must be 0 there. So that means a2 has to be 0. So that means we're not going to have any cosines in our final expression. Okay, by applying our boundary conditions, we've eliminated the cosine term. All right, now let's take the other one, psi at x equal to L. Now that, if we set that in, we have a1 now times sine of kl. All right, a2 is gone, so we don't have any cosine terms. Well, if we want that to equal 0, if we want a1 times sine of kl to equal 0, then that means if we don't want a trivial solution where a1 is 0, because we already said that's pretty trivial, 0 equals 0, no problem. But if we don't want that trivial solution, then that means that the sine part has to be 0. So that means that sine of kl has to be 0. When is our sine function 0? Our sine function is 0 when the argument is 0, pi, 2 pi, 3 pi, 4 pi, blah, blah, blah. Okay? So let's set KL equal to n pi, and that will make sine of KL equal to 0. And now we can solve for what our wave number k is. K would be n pi over L. All right? So this means that our wave function is a1 times the sine of n pi x over L. All right? So that's our solution to the infinite square well problem. It's a sinusoidal function. All right? Here it is. If our wave function is equal to a sine of 2 pi x over lambda, that's our general expression, okay? We know that k now is n pi over L, and k is 2 pi over lambda. So we have our wave function psi of x is equal to a, some undetermined constant, we still don't know what it is, times the sine of n pi x over L, okay? That's what we've got. All right, what this means is that there's restrictions on the wavelengths that are allowed for our particle in the square well. Okay, there's only certain wavelengths allowed. We'll talk more about that in just a second. We've shown here that our wave function, and therefore the absolute value of our wave function squared, is 0 at the boundaries, as it has to be continuous. But since it's a sinusoidal function, a sine function is going to go to 0 at other points inside the well, depending on the value of n. Okay? Now what we're going to show you when I show you the graph is how the number of 0 points changes as you go along. But before we get to that, let's talk about what the wavelength restrictions are. If you set 2 pi x over lambda, as we said what our wave function was, equal to n pi x over L, then you can see that there's only certain allowed values of the wavelength lambda. And that's when lambda is equal to 2L over n, if you solve, okay? Remember, L is the length of our box, and n is a number that starts at 1 and goes up in integer steps from there. What this means, if we've restricted our wavelength, that means that since p is equal to h over lambda, via our de Broglie wavelength expression, that there's only certain values of the momentum that are allowed, right? And that's nh over 2L. So we have restricted values of our momentum. Okay, we chose the potential energy of the particle to be 0 inside the box. All right, that means that the energy of the particle is just the kinetic energy, and the kinetic energy is p squared over 2m, okay? Now, if we plug in for p, and the p value, remember from the previous slide, was nh over 2L, then we can see that the total energy of the particle, p squared over 2m, is equal to h squared n squared over 8mL squared. What this means is that you have energy levels for the particle in the infinite square well. The energy of the particle is quantized, all right? Here's what the energy level diagram would look like, okay? The lowest possible energy is n equal to 1. That's our ground state, right? And then what you would have is you'd have a value h squared over 8mL squared. And then that would be your ground state energy where n is equal to 1. And then as you go up in energy, right, you would go up as n squared, okay? So the energy of the nth level would be n squared times your ground state. Note that it's not possible for a particle to have no energy. This is the so-called 0 point energy that we talked about last time, okay? It's not possible for it to not be moving. The particle can never be at rest. And the energy level diagram looks like this. The energy levels start off more closely spaced, but since it goes as n squared, they go up and they get further apart as n goes up. If you were to look at what the wave function looks like, it looks like this, okay? So here's your sine function, and the first ground state is going to be when 1/2 of a wavelength is occupied. The first excited state is when you have the full wavelength, okay? And then you have 1.5 wavelengths for the second excited state, and so on and so forth, all right? If you were to look at what the probability density would be, remember that's the absolute value of the square of your wave function, then you'd get this, okay? You'd get the single hump for the ground state, the double hump camel for the first excited state, and then add a hump for every state that goes up, okay? What does this look like? Well, there's no coincidence here that this looks like a standing wave on a string, okay? Remember, classically, if you take a string and you confine it, hold it steady at both ends, and then you pluck the string, okay? You can call the string's length L, and say that the coordinate system runs from 0 to L, then what happens is you get standing waves set up, okay? Standing waves get set up. You get constructive and destructive interference until only certain things survive, right? The boundary condition on this system is that the string is held fixed, okay, at either end. This is kind of like a guitar string maybe, okay, or the demo that we did in class where we had the vibrating string and the little light show that went on. So the interference worked to produce standing waves that looked like this. So here you have your nodes where the wave function goes to 0, and then your antinodes where the wavelength is at a maximum. I'm sorry, where the wave is a maximum amplitude, okay? The wavelengths for the normal modes for a string are lambda is equal to 2L over n, and that's exactly what we said it was for the particle confined to the infinite square well, okay? So it's exactly the same. So there's a one-to-one analogy between the classical wave on a string confined at both ends and the quantum particle infinite square well. So this is something, a theme, that's going to be repeated again and again and again, okay? There's situations that are going to happen where only certain frequencies or wavelengths of oscillation are going to be allowed, and that's called quantization, hence quantum mechanics, okay? Quantization is a really super common occurrence when you have waves that are subjected to boundary conditions, okay? And that's exactly what we've got in quantum mechanics. We've got particles that have wave properties and they're subjected to boundary conditions, right? Like being confined somewhere by some kind of potential energy, okay? Now, the particle in an infinite square well is not a very physical potential. It's not realistic, in other words. There isn't anything that I can think of that's actually an infinite potential, okay? You can always escape it, all right? But there are some potentials, like the confinement of a proton to a nucleus, for example, that are really, really close to infinite. It's a good approximation for a lot of systems. And that's why we still teach the particle in the infinite square well when we teach quantum mechanics. All right, now I can't emphasize enough, guys, how much you need to do the reading, okay? And you need to go back over the lectures and think about what I've said and maybe go through the math yourself and make sure that it makes sense to you after each lecture. The importance of studying this material outside of class cannot be overemphasized when it comes to getting into quantum mechanics, okay? So I urge you, watch this lecture again, go back over it, go back over the notes, read the sections in the textbook, make sure you understand. And I'll be back next week, okay, to talk about any further questions that you might have, all right? So good luck, welcome to quantum.